Hello, and welcome to our webinar today. This is part 2 of 3 of an acoustic webinar given from M+P International and Acoustic Research Systems. Please make sure your speakers are on, and this webinar is being recorded, even though the cameras and microphones are disabled by default. So if you do have any questions, please post them in the chat window or in the Q&A, and we will do our best to address them at the end. And if you lose connection, you can always just close the webinar and log in again via the calendar link. This webinar is titled Navigating the Challenges of High Energy Acoustic Testing for Launch Vehicle Fairings. And essentially what that means is we're going to cover some of the operational portions and digest a little bit of what it's like to actually run an acoustic test and for launch vehicle applications. So firstly, we're going to go over the data acquisition topics, the test levels and schedule, pre-test and safety, pre-test validations. We're going to talk about running the test with special considerations for running the test. And then we're going to start looking at data package and delivery. But first, I'm going to hand it over to Eric Friedlander, who's your presenter today. Eric is the CTO of Acoustic Research Systems, and he has about 22 years of testing experience when it comes to this sort of thing. So you're in good hands with Eric. Want to say hi, Eric?
Hi, Dale. Thanks. I look forward to digesting some information with you today. Uh, let's start on this first section on test levels and schedule. So next slide. Um, I think vast majority of us were here. We know most typical acoustic profiles, most typical direct field acoustic tests are driven by some sort of fairing launch environment. As you see here, there's several. Some of them, most of them are typically publicly available. There's a launcher manual for lots of them. The methods by which these environments are obtained and sort of the accuracy of the environments is fairly closely held by a lot of the launch vehicle providers. We're working with some to sort of help elucidate that a bit better. But where we're at today is you get a profile, you're told to test to it. There's also the fairing environment changes over the course of launch, but a acoustic test with a random uniform field is your best common denominator to capture sort of the most stressful potential environment that could occur during launch. That's sort of been the heritage approach to building confidence in that regard. One of the great things too about being able to test in third octave is you can also envelope multiple launch profiles. So if you don't quite know what you're going to launch on, you can take the loudest frequency from each of the, let's say, 3 launchers, make a composite envelope out of that. Upside is you're pretty much qualified on any one at that point. Downside is you are potentially adding additional stress and fatigue onto the flight hardware that might be above and beyond what we would see in flight. So there's always sort of a trade-off there. And then typically you'll test to 3 dB above your flight level proto flight. So they'll give you a flight level profile, maximum predicted envelope, and then you'll go 3 dB above that. That'll be your test level. But just bear in mind, with especially the decibel scale with that logarithmic curve, every 3 decibels is essentially 100% more energy. So that's not just energy imparted to the test article, but also energy required by the direct field system. So, it's easy to go from maybe 120 to 123 dB, but to go from 146 to 149 dB might be several order of magnitudes beyond that. So definitely something to keep in mind as you're starting the process. Next slide, please. So then the things to consider as part of the schedule. There's a couple sort of nomenclatures to keep in mind. We have sort of a test program, which is all of your acoustic test runs. Then you have sort of each acoustic test run, which turns on, ramps up to a predetermined level as part of your test campaign, and then ramps down again. And then you sort of you have a schedule within each run of what levels you're going to hit relative to the full level for that run in order to sort of ramp up it the way you want. So you want to sort of consider, first of all, how much time are you spending at lower levels? You start off at a -18 or a -12 of your 0 for that run. What I was saying earlier is bear in mind that let's say you're doing a -12 run, then 0 dB of that run is actually your -12 to flight level or proto flight. And then you might start at -12 dB below that to turn the system on equalize and ramp up. Dale will show you some slides of that a bit later. And so you want to consider your amount of time you turn on equalize, the amount of time it takes to ramp up. We're really fortunate using octave band control with that 1 second loop time. We're able to essentially just turn the volume knob up as the system equalizes. And so, in the past, if you had an old school sort of DFAT system with the concert speakers and you were using narrowband, you had to sort of jump between levels. It might take you several minutes just to get to full level, which if you're running proto flight means you're spending a minute or longer at flight level. You're sort of overexposing on your way to get to proto. So we're really fortunate to be able to ramp up, reach level within 20 to 30 seconds, run our full level, for that run, and then quickly ramp down and off. So it's important to really build up and bubble up the system. If you step up really hard and there's power issues or concerns with the building or the facility, you can potentially have facility issues. There's sort of anecdotal evidence of that. And then one other thing to just consider too is you want to kind of have your go, no-go criteria between each test run as well as for the overall test campaign. Sometimes it's easy for the test campaign to say good, pass or, fail. But between each run, it's important to have a little criteria defined as what you want to see, whether it's just survive or certain acceleration responses at lower levels correlate to a model. So if you do a -12 run, you say, okay, we've seen the things we want to see. Let's go to our -6 or our -3 run. Next slide, please. The other bit of it is just the logistics of setting up. This was a small system we're loading in a truck here, but there is time that it takes to unload from the truck, place everything in the room, and cable it. A typical small setup of a Neutron system, as an example, for a mid-sized satellite, maybe 12 or 14 neutrons, is a sort of 45 minutes to get in the building, 45 minutes to set up. If you start in the morning, you're ready before lunch. A large setup could take half a day. I do a lot of my schedules around meal times. So if you're doing a very large setup, you'd start at breakfast, take a break for lunch, and you might be done by dinner. And those are fairly efficient times, based on sort of what's out in the market today. The Neutron device, because it requires so much less parts and pieces, is about 50% faster to set up than a sort of typical concert system. But one thing to keep in mind is you're limited, typically, especially if you're stacking, you're limited by the crane. You can only set up as fast as the crane allows you, and that's just something to account for as you're wiring the system, sort of building amplifiers and control in parallel. Something that's really important is calibration. We talked about the other day, and just to be clear, we're talking about a handheld calibrator on site with your microphone before you start your test campaign. Getting a good calibration is really critical for a good acoustic test, as it is for any test. But if those mic cals aren't spot on, all your decibel information, everything that's feeding back to the controller is going to be potentially suspect. So that cal is really important. And then typically, as long as everything stays plugged in and you're in a temperature controlled environment, you keep that cal through the test campaign unless there's significant changes. Instrumentation, obviously you tap, check, and verify different gauges on the flight system, on the hardware, sort of beyond what the microphones are capturing. With the system we have, we're able to take everything in, all sensors of all shapes and sizes. So sometimes we'll calibrate mics, and then we'll do a tap check and vibe control for the accelerometers. And then when we run the test, all the mics and accels come together. We get nice aligned time histories for everything. And then the last thing to consider that some people miss is analysis time. No offense to any analysts in the audience, but it can take some time to analyze data depending on how detailed our customer wants to get. And so it's always something to keep in mind. I've sometimes sort of program management come to me and say, okay, when are you ready? And it's like, hey, I'm ready. Let's, complete the analysis portion first. So it's important to sort of budget for that. And the next slide. And then the last bit here is just keeping in mind something that we mentioned yesterday as we move through is as we're placing microphones and looking at data, we have these two sort of themes come to the forefront. One is the control microphone field, which is the same acoustic field, but as seen by the control mics. And then the array microphone field, the measured field, which is kind of the same acoustic field, but as seen by the monitor mics. And again, we're talking discrete locations. We're talking sort of quality assuring what the control mics are seeing. And having that array field, it should look the same as the control field. And so if you end up in a situation where your control mics show one thing, but your array mics, your monitor microphones show something else, if you don't have agreement between those two sort of visions of the field, then you're not necessarily getting a good quality of test. So next slide, please. So next section we're going to talk about is pre-test safety. And that's something that we talked about yesterday as well. Next slide, please. You know, I wore my Viper shirt today. A lot of what we talked about yesterday in facility and building safety process, we got to pilot in partnership with NASA as part of some of the hardware that we're testing for them coming up early next year. And a lot of these safety steps were just not covered in Handbook 7010. So we're trying to help build a sort of generically applicable objective process for acoustic test safety, you know, within the facility. So first thing to consider is just microphone preparation. We talked about yesterday, calibration. Vibe Control has a great automatic cal process where you set it to calibrate mode. It sits there and listens, and then an operator can go into the circle and just stick that calibrator on each microphone, couple seconds, 5 to 10 seconds a mic. It's really easy to bang out a whole set of 30, 40 microphones in a few minutes and have everything caled, ready to go for the test. You also want to be mindful of heat from not necessarily acoustic devices, but if you have a active loudspeaker, something that's the amplifier built into the cabinet, you're gonna have a lot of heat and high powered electronics, very close proximity to the test article. And then some amplifiers generate a lot of heat, you know, when they're in idle or when they're sitting there waiting between tests, and they can actually influence the ambient temperature of the room. So you want to be careful that you're choosing a system that is efficient, doesn't generate a ton of heat, or you're placing it in a separate location. Next slide. Then as far as your initial systems checks, this is an example from our setup, but you know, we've checked that everything's plugged in and sort of has a home in the right place. We check our system processor. You can see it on the right that everything's muted and safe. And then we check that our software is synchronized to the amplifiers, so we have real-time control over network of the system. There's safety and room announcements that'll occur, not just before the test, but also before we energize the system. Once the amplifiers are on and energized, you know, the risk of an anomalous transient through the system is extremely low. But as a best practice, we always try to minimize people going in and out of the circle once everything's energized, just out of an abundance of caution. And we'll walk through people and do tours around the system, let people work. And obviously it is safe to work in the middle, but so we try to sort of take an extra safety step there with both 2 mutes and also reducing folks in the middle. And then obviously when we're getting ready to run a test, there's a whole tree and a process that happens, which I'll talk about. So once we've sort of looked at the acoustic system is online and muted, and we've done all our sort of pre-test checks on that side. Next slide, please. The next step is the loop check from the controller. So this is a really cool feature that M&P implemented for us on the ARS side. And it allows you to verify the integrity of the entire signal chain, front to back, soup to nuts, from source all the way to control mic and back to the controller. So what this allows you to do is spit a little bit of random noise outside of out of each drive discrete serially, not parallel. So it checks each one individually, goes around the whole setup, and then it verifies as noise emits from the acoustic device that the microphone is capturing it and that it's patched properly so that the right control microphone is hearing the right source that we talked about yesterday. So you can see there on the right, a successful loop check. Everything's green all the way down the line there. Each source has a control mic that's hearing it. And the great thing is it's a great confidence builder, not just as a pre-test verification, but also if we've got really sensitive flight hardware in the circle, program doesn't necessarily want to just turn on and go. They want a verification the system's ready, and this allows us to sort of provide that within under a minute. But I want to be clear, this loop check is not a sort of shaping or pre-equalizing. You know, with some systems, you have to sort of run and shape and acquire the phase targets and then choose microphone. You know, you don't have to go through this lengthy process to pre-calibrate the system. This is simply a verification and check. Next slide, please. And then as I mentioned earlier, sort of pre-test safety considerations. This is a tree that we've started developing. We actually did this for a client, and we're building it. But sort of this idea of not just what announcements are we making, but who's making them and who's on headsets. We supply sort of pit crew race style headsets for certain people around the building and the test setup. It's a hardwired analog line, so it doesn't have any security or any sort of digital wireless concerns. But it allows people to talk in real time. We have a certain number of people on there in certain key locations to monitor doorways or monitor parts of the facility if safety wants to keep an extra set of eyes. Even though a sign might say acoustic test in progress, do not enter, that doesn't mean that sign is 100% effective at preventing people from entering. So sometimes a person needs to be there for everyone's safety. But another thing to consider too is you got a couple people on headset, your test conductor, your operator might be off headset with the conductor sitting next to him. You're going to have a certain number of people who are authorized to call an abort. So if they see something wrong, if there's something anomalous from a safety standpoint outside of the actual acoustic test, then they can call an abort per sort of the customer's test director. We also have a manual handheld abort switch that somebody can hold and they can actually fire that, and that will shut down all the amplifiers instantaneously and just bring everything to a quick ramp down. And then ideally, we get through the run, we're clear, and then we give all the current headset. So there's several different ways to sort of handle that. And the other thing too, I'll just mention is to low level runs. When we first turn on the system and when we do our first run, the levels in the circle are barely above what you would get at a rock and roll concert. And so what we do is start at these low levels, get everybody comfortable, and sort of build confidence in the safety plan. There's sort of perception that when you turn the system on, it just bangs out, the sound of a rocket launch. And we try to give people, sort of this perspective that, hey, we start at low level, we gradually ramp up, we build confidence, not just in the safety plan, but also in the behavior of the test setup and potentially the flight hardware and mass model. So it's really easy to ease into this conversation from a safety and operations standpoint. Next slide. And the last kind of point I'll make on the practical considerations of loud testing in typical facilities. This is a photo of our facility here with this beautiful large hangar that we've retrofitted into our test facility. We do demonstrations and R&D here. Occasionally we test customer flight hardware. As far as I know, I think it's the largest sort of direct field test facility, at least in the country. And we regularly do tests here in the 140 to 150 decibel range. And this is close to a typical high bay at a aerospace company. It is exposed rafters. We have exposed pipes. We have windows, sprinklers. We did our safety analysis before moving into the building several years ago. And then we've monitored the facility, looked at pressures and pipes and sprinkler systems. And we, over the last 3 years, and I mean, 3, maybe even 400 different acoustic test runs in this facility up to, like I said, 150 and more, we haven't seen any sort of concerning anomalies or any sort of delta between in like the sprinkler system or natural gas system since when we moved in and today. So that gives us confidence, allows us to give our customers some confidence too that, again, an acoustic test is allowed, but the force and the pressure it imparts on the facility and where it's at is significantly less than what's happening in the middle of the circle. And I think some of you know too from your background, something can only shake or move as much as it's susceptible to being shaken and moved. And most buildings are not susceptible to being disrupted by a test like this. So we found that to be the typical case, but as you saw earlier, we kind of have a process to work through and kind of get to point where everybody feels confident and all the facility folks are happy. So next slide, please. I am going to now hand over to Dale to talk through some of the pre-test activities from the controller side, and then some of the actual, we're actually getting into running the test. So Dale, you want to take it from here?
Yeah, thanks, Eric. So prior to going through the exercise that Eric just described, There's a couple things that we like to take a look at, and we encourage you to take a look at for your individual data acquisition systems and control systems. At ARS, they use the M plus P vibe control system. And for this, both the control and data acquisition hardware follow a regular calibration schedule. And for us, because this is not an adjustable hardware, it's basically a performance verification. So what we can do is follow the NIST, or which is acceptable in most facilities, or we could follow the A2LA or ISO 17025 standard. And we basically compare the voltages for a calibrated standard to the voltage inputs for each individual channel, and also the voltage generated by the source. So what that does is essentially proves that the source output, which if I could turn my laser on here, the source output coming from here is properly generating a voltage signal at various frequencies, and the input here is also reading the same voltage signal within some calibrated tolerance, and that tolerance is very fine. The performance verifications for hardware, again, doesn't require the adjustment of said hardware, but what it does do is it allows you to even retroactively prove that the hardware was functioning when you're doing a test. So even if you did a test, you found out afterward, oh shoot, I wasn't calibrated for that test, you theoretically, with a performance verification, could go in and determine whether it's reading correctly now, because if it's reading correctly now, it was reading correctly prior to. And the calibration intervals for this are typically a year, but they're set by metrology or by your customer. So if you're flying on a ULA rocket, and ULA rocket says that you're required to have yearly calibrations on all of your equipment, then this is the system you should follow. After calibration, however, it's best to follow the hardware's connectivity with the overall system in an intrinsic configuration. And what I mean by that is to run by wire, or we call it closed loop, in order to verify the source outputs. What you would essentially do is run a short cabling from each source to each input, just as you would be kind of verifying the loop. So just as I show here, you'd be running by a single wire for each particular source. So if you have 24 sources going to 24 separate neutrons, you'd have 24 of these cables set up from the sources to the inputs. And what this can do is, by using very short cabling, then using the final test cabling for an A to B comparison, it can help characterize the signal loss of your long cable runs. And this can verify that, if you're running 100-foot cables from the microphones to the system, that you're not getting a whole lot of signal loss. And overall, problems like this can be easily identified, and the system can be configured locked for testing, which is a safe way to test. So the way we recommend to do that is, once the configuration is locked, and by the way, locked is a figure of speech. It's not like you actually put a padlock on it, but it's more of an engineering lock to determine that no one is doing any major software updates or configuration changes to the cabling or changing out cabling runs unless it's absolutely necessary. Because then the locked configuration can be confirmed by the quality assurance department if necessary, to give more confidence that you can move forward to test with your system. The control hardware can also accept safety conditions or external triggered systems when needed. Kind of like Eric mentioned, if there's a physical abort button, the person allowed to use that could jam on that button and it could shut down the drive. I think on the ARS drive, this actually shuts down the amplifiers directly. But if you were running a shaker, or you wanted a separate proof shutdown directly to the system, on our system, we would basically have a little jumper right here. This is a normally closed circuit. So when this is installed in the system as normally closed, it enables the system to run. If you were to open that at any given time, that would put the system in a soft shutdown, which can shut down the system anywhere between, I think, 10 to 1,000 milliseconds. Another thing to consider is the protected earth ground, or PE ground. So when ground isolation is an issue, it can affect the control signals, or it can exhibit non-existent noise that shows up on the inputs. So that could be on microphones, it could be on accelerometers. And the protective earth ground can tie the control system to the system ground of a common source, such as the spacecraft or a building ground. And this can eliminate ground loops before they become a problem. Also, though it's not a safety issue per se, external control systems or external data acquisition systems or other types of telemetry systems could be triggered upon various control states. So those very same digital inputs that you used for the external shutdown can also provide TTL digital inputs and digital outputs. And a couple of those running states are basically turn on and off the TTLs that can trigger other systems. So for instance, when the test is in standby, one of these is turned on. When the test is in run, another one is turned on. And when the test is at 0 dB, yet another one is turned on, which shuts off at the end. And that could trigger a linear average, for instance, on a separate data acquisition system if you have such a thing. Additionally, there's tolerance conditions that allow a test to continue from within the software. There's tolerances for microphones, octave bands, and overall sound pressure level, and those can help ensure that the test is viable before the test article is even introduced. Some of these test specifications, the test specifications from the launch manufacturers might actually have requirements for these parameters, so be on the lookout for those as well. Mass models can also be used for pretest validation, and that can give confidence that the power output of a given system is adequate to excite the levels that you're going to do during the real test. So as a pretest operation, it can help the actual test go a little smoother because you've done kind of a mock run. However, mass model testing is not necessary for the system that we are proposing because the octave control algorithm actively controls changes in the pressure field up to once a second. And as a result, we don't need to shape the actual field in order to replay it or reload it at a later time. It doesn't matter what we put in there. We could put, a shoe hanging from the middle and then control to that and then put a spacecraft in after, and it's going to control just as well with the shoe. So also note that the blankets down here, these are acoustic absorptive blankets. These are actually optional, but they were used when the reflections from the dolly that it sits on, it's like a big diamond plate pattern. The reflections from that were actually causing some issues with the phase targeting of the narrowband system. But again, with this system, these blankets down here are not typically necessary. There's some things to avoid where mass models are concerned. Certain control systems that replay full level tests from a shaped mass model may not be able to adequately control changes in the field if something were to change or break. And it's sad when this happens, but sometimes during testing, you find out that there's a design flaw or a manufacturing flaw, and something can break and make changes to the reflections in the field. And if it can't control or adjust to that, then you might have an even bigger problem. Yeah. So whether or not a mass model is used, it's time to examine the actual running of the test. And thankfully, this is probably the easiest part of the test. This is because there's two primary protection systems within this proposed system. The ARS drive has its own limiting system, which prevents the user from damaging the drivers or amplifiers. And the M+P control system makes pretty light work of testing for any device, small or large. When running the test, the operators are presented with the test control telemetry and DFAN system performance telemetry. Most importantly, the acoustic devices can be monitored to ensure the controller isn't pushing the amplifiers into a voltage or current limiting state. And you get real-time indicators that show the output of the system relative to the max capability. So this can make you decisions as to how far you can push the system in subsequent tests. There's also active impedance monitoring, which shows the thermal trending of the system and ensures that it's in nominal operating range. And the test is highly automated here. So if you look over to the left where we have the protection limiter on set, this is just something you can monitor. This is essentially automated. Once you hit the unmute button on the system, it just goes. Safety limiters and responsive readouts are also combined with the control readouts that are shown over here on the right on the M+P system. And that indicates that the system is running in a smooth and controlled fashion. Just before we get into the actual operation of the test and what to look for, it's important to consider this schedule that Eric mentioned earlier. So when stepping up to full level of the test, the lower level shaping is pretty important. because it helps define the actual curve here that you see on the spectrum requirement. So lower level tests help to verify the equalization of the octave bands here. They also help to the linearity when each level steps upward. They help to keep the equalization before 0 dB as brief as possible by providing the best shape before stepping up to it. And they can be loaded or stored to help speed up the pre-level tests. And what I mean is I could create a shape just before the test at a very low level, like in this example, we have minus 24. And once that shape is achieved, I can save it as a file and then load it so that I only need to spend, I don't know, maybe a second or two at that level at minus 24 before stepping up to minus 3 dB. And if you load it at a lower level, it is uncontrolled, but while you're stepping up to the higher level, it's absolutely in control of the system. So it's kind of like the best of both worlds for pre-shaping and for actual operation. So additionally, a lower level test can verify the capability of the system and verify the measurement hardware readiness. And this is a good thing to try out. As Eric mentioned, you're going to have these separate tests, test levels from within the full level test just to kind of verify functionality. And that's kind of what we're talking about here. So in this example run, we can see that less than 40 seconds are dedicated to stepping up to full level test. That's really fast. You know, there isn't a reverberant chamber on Earth or even probably some of the legacy DFAN systems that are out there that can step up this quickly without risk of damaging something. So the 24 dB portion here from the full level test is dedicated to shaping the acoustic field essentially right here. So that you'll see that a little bit later when we actually run the test. And ultimately that only required about 15 seconds, probably maybe even less, but we scheduled it for 30. So that's what we're accounting for here. So then the 3 dB portion can be seen here, and you can see there's a nice slow gradual ramp up. Right, you can't see my mouse, but you can see this. There's a nice slow gradual ramp up here, and that's really important because if you see just a hard shelf here that's stepping up, that very rarely takes into account the nonlinearity of the acoustic field. So when you're looking at time history data, this is a great thing to look for. But yeah, the minus 3 dB portion only required a little bit of time. Then you can see that the 0 dB portion here, we only scheduled it for 30 seconds because this was a ramp up experiment, but this could have been, you know, a minute, 5 minutes, 20 minutes at this level. It was pretty low. But that's what you want to see is this nice gradual build up. So there's three primary plots to monitor when you're running a test, and here you actually see a vibration or a acoustic control test happening real time. So the time constant in this case is 1 second. And though the test operator is encouraged to monitor this, the system really takes care of all the adjustments. And the need for a user to intervene is extremely rare. It's usually only when there's an equipment problem that this becomes an issue. So this is the control signal, right? It's adjusted based on the compression speed setting. And electrodynamic drivers, such as the Neutron, are really consistent in their ability to accept adjustments. So compression speed doesn't typically need to be modified from test to test. It's usually something we set for the acoustic test company, and then they run with it. The control plot balances the responsiveness of the drive with the highly dynamic measured acoustic field. So it's advised to avoid systems that step from lower levels in an instantaneous fashion. As you can see how this system actually just kind of bubbled up from the lower levels. This is a nice even way to account for the nonlinearity of the acoustic field. And what's happening on these other systems that step up immediately is that they're basically built from a random vibration control system, and that's designed for the mechanically coupled electrodynamic shaker. So it assumes linearity when stepping up. So the second plot to keep an eye on is the drive level. So this is the drive output that you saw that we did the run by wire a little bit earlier. That was the drive output, which sends the acoustic signal in third octaves directly to the amplifier. Characteristics of this signal are that it should equalize at each test level in accordance with the control. It should not approach the maximum voltage output of the hardware, which in this case is 10 volts peak or about 3.5 volts RMS up here. As you can see, this is a relatively low one. Fortunately, indications of problems that should be avoided are easily spotted on the drive. what'll happen is if one or more of these octave bands is increasing in level continuously, even though the control level does not, that means that the octave band has achieved its efficiency limit. And you also want to look out for an overall unpredictable shape from one run to another, as it can indicate problems or inefficiencies with the system. Lastly, the error plot can reveal not only efficiency issues as with the drive signal, but also stability. So similar to the drive, the error should equilibrate to within plus or minus 6 dB or so for each level. This one's a little tricky though, because since it's adjusted every second, it can kind of quickly indicate if there are problems, sometimes even before the other plots do. So you can see this changing every second. This is after we've stepped up to the second level, but we have a range here of 10 dB, and it's staying about within 2 to 4 dB. Now here's where we step up level. You can see it. The error is very low, so the control system is making drive adjustments in order to bring that error back up to 0. And here we are probably equalizing at 0 dB. And you can see there's a little more variation at low levels. This is very common because of the low frequency waves and how they propagate. But on the higher frequencies, you should see this really close to 0. And what this means is this control system, every single second, is making these drive adjustments and making and adjusting to this error. And we can change the compression speed and also change how quickly we want to react to that, depending on how you want the system to control. So if the overall shape or level of this is unpredictable, that can be a sign of instability or inefficiency in the system. So we focused on each of those three individual components, the control, the drive, the error. So let's take a look at how they work together in a test to basically make a stable acoustic control system. So here they are all together. What I'm going to do is I'm going to start a test here. And I've turned on the throughput, which is taking time domain for all of the response accelerometers on the spacecraft and the microphones in the field. So every channel coming in has its own throughput. And you can see we started the test and the control is building. And this is where I'm talking about the minus 24 or minus 12, wherever you're starting. This is where it equilibrates, right? When all the octave bands are green, then we can choose to make a decision to step up to the next level. So here we chose -6. You can see that right here. And you can see it slowly bubbling up there. You can see the changes in the error. The error stays close to 0 when this is reached, when this is finally equilibrated. So here we are up to the next level. All the bands are blue. We're moving up, and here they are. Started the test level at 0 dB, and then it's going to run for a solid minute there. So in this example, the control system is not only adjusting the drive from the error in the control measurement, but also recording the throughput. And with modern control systems, many of these incoherent sources, like for the ARS system, they've done 48 or more. This can be controlled while also taking data and processing for hundreds of response channels. So in this kind of system, your control system can actually act as your data acquisition system. There's also ways to set up the data acquisition system separately so that it is limiting on channels and monitoring these things, and then it can use that enable loop that we talked about before to shut down the controller. So you could have redundant systems both recording similar things, but they're challenging each other to stay in spec. Speaking of response data recorded by that throughput, it can be useful to display the PSD plots from all those response accelerometers alongside the primary control loop to help make decisions about the efficacy of the control. And to do that, you can look at the general health of the device under test, as you can see here. Right, so this is the power spectral density in a linear average, as we can see, because we hit the measure button here. So that's why it looks nice and smooth and it's not changing a whole lot, because it's actually compiling a true linear average of that full level there. Right. So it's important to capture that throughput data to disk because for these measurements, in order to verify the measurement accuracy. We always say kind of like trust but verify, right? Your control and data acquisition system, if you're using us, if you're using another vendor, they should be providing you with that data so that you can make verifications that it is what they say it is. And these can be monitored real time also for frequency shifts, right? So if I was looking at these data channels, and we'll talk a little bit about this in the webinar tomorrow, but if I was monitoring these data channels and I started to see a frequency shift at full level, that's something to be concerned about, unless it's some kind of mechanical device that the frequency is going to shift for the resonances. this is something that would be an abort condition for the test. So really, that's it. We ran a test. This is what it comes down to running a test. You're basically turning it on, you're monitoring, you're verifying that everything is reading nominally, and then the rest of it is just looking at the data afterwards. And there's some special considerations for that data packaging to examine. Firstly, for some tests for which the goal isn't flight qualification, like for a specific launch envelope, notching or limiting for specific narrowband sections of the field may be necessary to attenuate the responses. So I should note that for a flight qualification test, this practice can basically invalidate the test and should only be applied for special cases. In the example shown, we have a panel with a known resonance at about 120 hertz, and this is notched by lowering the energy in the field only for that given response. You can see that here. On the left, we have the unnotched response. This is just a basic, relatively flat or shaped acoustic profile. And the field is essentially shaped to create an artificially specified response on the test article. So in this example, about 100 G squared per hertz field at that particular point in time in the spectral domain is notched down to 1 G squared per hertz at the peak. So that's roughly a 20 dB reduction, which is pretty incredible. And that's where you can see the reduction here on the right-hand side. So in these types of tests, an effective notch is capable of reducing the acoustic field more than 3 dB, as the system is not reliant on the neighboring devices to produce the overall power. And more interestingly, there's an option to keep the third octave control within the specification by increasing neighboring frequencies. So this way, the response at the critical frequencies can be reduced. As you can see up here, we've reduced that little notch there. But when you look at the third octave plots for the control, they look almost identical. So it's been notched, but you still maintained your test requirement. Secondly, it's possible to control each octave band in open loop. This is a very experimental thing. We've never even had to do this with the ARS neutron system because it just controls well enough and is efficient enough. But if you were doing an experimental test where you wanted to just take a couple loops, open up their control algorithm and just turn them up or down, this is a possibility by selecting the octave bands to control an open loop down here with the little checkbox. We can then boost the frequencies just like you could on your car stereo EQ. And again, this is not typically used for launch qualification testing. It's just a special thing you can do. Thirdly, you can do special or iterative tests. Those can be programmed in sequence by using the advanced VibUtils program. So the user can define multiple tests, profiles, and sequences up here in the scheduler. And then these can all be programmed to alert users when they are complete here. They can send a status email to somebody when a problem occurs, such as a loss of power. And additionally, within the tabular programming environment, this digital input and output, this can be programmed to manage exterior devices through the same digital I/O that we were talking about before on the VibRunner hardware. So this could be an external data acquisition system, like an independent watchdog system, such as a current limiter, for example, or it could just be facility equipment. Lastly, there are many tunable features of the control system that can be preset for a certain facility, and this locks in their functionality and makes them the general operation of them foolproof. One of them is rolling averages, and this can be automatically recorded and saving basically as a saved post-test operation. And then you don't have to do it. You don't have to do it in post-processing. You can verify that it was done, and you can verify that it was done properly. But once you get that process rolling, it's just there. And that's what you can see right here. This is a 1 second time constant rolling average of an entire 60-second test. So you can see how stable the control is and make decisions about whether to move forward. You can also adjust the compression speed, and this is how quickly the drive makes adjustments below the spectrum and above the spectrum. And you can also adjust the nonlinearity factor of the acoustic field. Though, again, we haven't had to do that with the neutron system because it's relatively efficient within the region. And that efficiency has made this setting basically, it's basically obviated the setting. So we've run a test. Now what? Right? There's typically several tests to run, and some are at lower levels than others. So there's a couple things that we want to take a look at after we've run this test. And once that data has been processed, we want to take a look at the acoustic field itself, right? And we can do that via third octave measurements to ensure that they're within tolerance and that the control field is similar to the measured field, as we had showed before. The spectral data is also really important, shown here. This ensures that there's no obvious deviations and also to ensure that the control field is similar to the measurement field again. So we would look at both controls and all the monitor mics unaveraged, unsmoothed, all together on the same plot with abort and alarm traces in order to determine that. And lastly, but I think probably most importantly, is coherence. We look at the coherence, both individually and averaged, and this helps to ensure the uniformity of the rest of the field where it cannot be measured, because you can't put monitor microphones in the spaces occupied by the spacecraft and everywhere else. So we use coherence to ensure that the field is more like an ideal diffuse acoustic field. Yes, we actually covered rolling averages. So I'm going to skip this one and move forward to the predicted responses. So the predicted responses of the test article are also compared to the analysis response. And this ensures that the test article is equally excited, right? If some modes are not excited properly, the acoustic field may not be uniform, as hot and cold spots can over or under excite specific modes, as shown here, right? And these predictions can come from a variety of analyses. An impact modal test, can use a tuned force hammer excitation and an acceleration response to produce frequency response functions. And this can reveal individual components of the dynamic response. And the shaker modal test does basically the same thing, but with one or more shakers. If you don't have access to an actual modal test, you could use finite element analysis, which is predictive, but that could be a low-cost alternative to measured results. Even vibration testing on its own prior to the acoustic testing can reveal the general modes of the system, but keep in mind that's within the boundary conditions of the fixturing, which might be a lot more stiff than what you would see in flight or on a typical mounting condition. And some combination of these methods, I think, can produce excellent results when comparing to the measured response of an acoustic test. So if you're a startup and you're making new experimental spacecraft, you do what you can. You do what you have capability to do. And some minor mixture of a little bit of modal, a little bit of FEM correlation, and vibration testing prior to your acoustic test can go a long way. Now, as a preview for tomorrow, I'm just going to go over really quickly what we might want to see at the end of a vibration or an acoustic test rather, and why it's useful. And then tomorrow we're actually going to go through those data processing. We're going to do a little bit of live processing, and then we're going to hopefully there'll be a few more questions about how that data is processed and what we're doing. So what the test analyzed, this is one of the first considerations. This is the even though we have the octaves and those provide a special confirmation that the levels were met, they don't always indicate how stable the overall sound pressure level is. So plotting overall SPL over time for all microphones is a great way to determine the stability. This can be done automatically in the Vibe Control software and is saved for every test, and then it can just be exported to MATLAB or ASCII format. And what you're really looking for, very similar to the time domain, but this is an overall SPL, is you have the start of the test measuring the room noise. You have a nice smooth transition up to the first level and the subsequent levels. And then when you get to 0, we don't see any drifting or anything falling out. All of the control microphones in this case they were all monitor microphones, but all the monitor microphones maintain the required SPL level as required by the launch manufacturer. Maybe even more important than the OSPL is that time history recording we mentioned before. This is what I recommend to trust but verify the data from your acoustic provider or test lab. And if they've properly acquired the time domain data, it can help you do just that. So from the recording, you can process almost anything. I could reprocess this time domain region as a linear average or an exponential average to compare which was provided by the acoustic device provider. I can also reprocess it at a higher or lower resolution to take a look at that. I can change the time constant and reprocess from third octaves. And I can also reprocess all of those microphones in the field as excitation devices to obtain principal input spectra, and that can give me the coherence for any of these items. So what we would do there is we would essentially compare microphone 1 with all of the other microphones in the system. So if you had 48 neutrons, you would probably have 48 microphones. Microphone 1 compared by all other 48 will give you 47 individual plots. And those 47 plots will provide that coherence measurement that I showed before. So then we have, lastly, the octaves. And that will give you the average of the entire 0 dB exposure. And that's a linear average, right? It's really important when you're looking at the octave data and the PSD data to ensure that what this spectrum here is drawn by a linear average from the full time history. And what I mean by that is the averages starting here will matter just as much as the averages here. Because if you do an exponential average, the averages at the end of the test matter quite a lot and then exponentially decay in how much they participate in the final average as you get further away from the beginning. So you want to make sure this is a true linear average, and that you can see that by either the degrees of freedom on the PSD plot, or you can see that as specifically noted as a linear average. Because exponential average, as I mentioned before, it really only provides like a final snapshot of the data, and that can hide issues that can crop up over the test. You also want to, this can be used every 4 seconds to calculate the rolling averages that we mentioned before. And some specifications require 8 seconds, some require 5, some require 4, some even want to see it down to 1. And any of those can be preset in the software. And again, the X and Y plot is really just octaves over dB for this case. So that's the end of our webinar. As I mentioned, or maybe did not mention, we have a third one tomorrow. And I've placed the link for that in the chat. So if you did not register for the third webinar tomorrow, please have a look at that and utilize that link in the chat window, or you can always email us at M+P or ARS for any of that additional information. So I'm going to take a look here, see if we've got anything in the chat.
Yeah, if anyone has questions,
Yeah.
This is a great time. And also, if you think of anything in the middle of the night, we can definitely answer them tomorrow.
Yeah. Did you have anything additional to add there to the data packaging? Have you seen anything out there, Eric, with in terms of requests?
I think that's great. I think the majority of the issues we run into is just a lack of consistency. You know, there's some agencies that have a lot of institutional knowledge on data processing. There's others that are newer to it, and there's not a ton of good guidance out there. So we're trying to at least be consistent from our side. We found that I think the data sets we provide are really, I mean, when you provide time histories, that's the most transparency that you can offer, and that's sort of always been our goal from day one. I don't think that is necessarily employed by everyone, but yeah, I mean, once between the time histories and those typical plots you showed, we haven't run into a situation yet where there's not enough confidence in the performance of the system and the achievement of the test.
Yeah, I've noticed that some facilities that have reverberant chambers, that the expectation for data is much higher. You know, like you take some of the NASA facilities, and they're used to characterizing the room modes of the reverberant system and looking at the instability of the lower frequency horns, looking at some of the lack of the higher frequency generation, because it's just free energy being generated from the air pressure in the reverberant chamber. A lot of those customers are more demanding on, that they need time histories for every single thing, and they're going to post-process everything for their own stability. And I think that's great. I think that's a model for how any startup company could look for a data package. It's basically to say, I want that whole thing. I want all the data I can get.
And I think you made a good point too. We talk about averaging a lot too, because I think the previous practice before we started down this path was, the vendor would sort of hand over a piece of paper and there was a line down the middle sitting on top of the reference, and it said, okay, this is it, we did it, and that was an average an average of all the averages of all the exponential averages,
which is smoothed.
So just smooth. So you're dealing with a random signal with a significant crest factor. So it's important to look at the averages to understand sort of the total energy imparted and sort of what it averages out to. But it's also important, like you were saying, to look in those sections and understand, kind of see how it behaves within those segments to make sure that those all kind of line up to tell the full story. It's not a sine wave, right? But it's also, if you over average, it's easy to obfuscate issues, especially at the tail end beginnings of tests where you might not have had enough control loops to make drive adjustments yet. And especially at the end, if your system is screaming across the finish line and it's hitting limiters, then you might see it stagging towards the end of the test, and some averages might obfuscate that. So it's good to have a balance of both.
Yeah, good point. Cool. Well, I think
yeah,
we'll finish up here. We'll let
so.
everyone get on with their day, and hopefully we'll see some of you at the Data Processing Fest tomorrow for our webinar. And thanks everyone for your attendance. We appreciate you. Have a good day.